So this is the introductory talk for discrete subgroups of Lie groups, and we would like to provide you some motivation on why one should care about discrete subgroups of Lie groups, and some more background on a particular class of such groups, which are called Anosov representations. And first, let us recall that a subgroup gamma of a real Lie group G is called discrete if there exists an open neighborhood U of the identity which intersects gamma at precisely the identity element. And in general, Lie groups have lots of associated algebraic and dynamical and geometric structure, which in fact is inherited by their discrete subgroups and the quotient manifolds of orbifolds. And moreover, many examples often arise through geometric structures on closed manifolds that one would like to understand. So that's the case for hyperbolic structures on closed orientable hyperbolic surfaces. And now let us provide some classes of examples, which of course this list is very far away from being exhaustive. And first, a famous class of examples are lattices in non-compact real semi-simple Lie groups. And from the point of view of the representation theory, it was a breakthrough of Margulis in the early 70s that if gamma is an irreducible lattice in a higher rank Lie group, then its linear representations are well understood. So what happens here is that essentially, if you take a representation of gamma over R with, let's say, non-precompact closure, essentially that representation comes from a representation of the whole Lie group G. And representations of G are well understood. And the basic example that you could have in mind is the case where G is the special linear group over R, and gamma consists of all determinant one matrices with integral entries. And in the exact opposite direction, we have fundamental groups of closed hyperbolic surfaces. So if you put a hyperbolic structure on a closed hyperbolic surface of genus G at least 2, then you obtain a representation of the fundamental group of the underlying surface into the isometry group of the universal cover, which in that case is the two-dimensional real hyperbolic space. And in general, surface groups have lots of interesting discrete faithful representations. And another class of examples are Kleinian groups, which refers to discrete subgroups of the isometry group of the real hyperbolic space when n is greater or equal than 3. And there are many such types of Kleinian groups, for example, convex or compact and geometrically finite. And lastly, we would like to mention here the class of Anosov representations of Gromov hyperbolic groups. These were introduced by Labouri in 2004 and further developed by Guissard and Winhart in 2012. And in general, this is also a very rich class of discrete groups, discrete subgroups of Lie groups with interesting dynamical properties. And we will give in a bit the definition. But before that, we need the notion of the Gromov hyperbolic group. And when gamma is a finally generated group, and we fix a finite generating subset, which by default we assume that it's closed under taking inverses of elements, then we can form the Cayley graph of gamma with respect to S. So this is the graph where the vertices are the elements of the group, and you have an edge between two vertices if their difference is an element in S. And we can put the metric ds on the Kelly graph by simply, which is simply like the usual path metric, giving length 1 on each edge. And now having the Kelly graph and a metric on it, we will call a group gamma Gromov hyperbolic if its Kelly graph with that metric is a delta hyperbolic space for some uniform constant delta greater or equal than 0. So that means whenever we take 3 vertices in that graph, or equivalently 3 elements of the group, and we take geodesics joining the points, so we form a geodesic triangle, then any of these 3 geodesics lies in the union of the delta neighborhoods of the other 2. And the notion of Gromov hyperbolicity is independent of the choice of the generating set. And let me also mention that Gromov hyperbolic groups were introduced by Gromov in 1987. And here it's like the picture of where we try to give you a picture of delta thin triangle. So you can see here that the delta neighborhoods of any of 2 geodesics in that triangle covers the third one. So all of these are the delta neighborhoods. And let us provide here now some examples of Gromov hyperbolic groups. In general, this is like a very big class of a big and rich class of finely presented groups. And the simplest examples of Gromov hyperbolic groups are free groups. So if we take the free group on K generators, A1 through AK, and we form the Kelly graph of the group with respect to the generating set consisting the free generators and their inverses, then you can see that this is a tree. And it's also 0 hyperbolic with the path metric. And therefore, the free groups are hyperbolic, of course. And the next more complicated class of examples are fundamental groups of closed hyperbolic surfaces. So if we take the surface of genus G, where G is at least equal to 2, its fundamental group has a presentation of that form. So it is generated by 2 G elements with a single defining relation, the product of all these commutators. And this fundamental group is also Gromov hyperbolic. And this is because, in fact, with many ways you can realize the surface group as a discrete subgroup of isometries of the 2-dimensional real hyperbolic space. And the surface group acts co-compactly, in fact, on the hyperbolic space, equipped with a distance coming from the usual Riemannian metric with curvature -1. So because this space here is Gromov hyperbolic, this automatically is inherited by the group which acts geometrically on that space. And for the same reason, whenever we take a discrete subgroup of a real rank 1 Lie group, which is co-compact, meaning that the quotient space is compact, then this group acts also co-compactly on the symmetric space of G, and with an appropriate metric which the group preserves, that symmetric space is hyperbolic, and therefore the group itself is hyperbolic. So now we would like to provide you a very basic construction of discrete subgroups in Lie groups, in fact in isometry groups of real hyperbolic spaces coming from ping pong. So we fix G1 and G2 to hyperbolic isometries of the D hyperbolic space. So you can see here the isometries G1 and G2 have fixed points G1 plus, G1 minus, G2 minus, G2 plus at the Gromov boundary of the hyperbolic space. And yeah, we assume these fixed point set are disjoint, so all these points are distinct. And then it is a fact that we can choose a large enough natural number n, and disjoint open neighborhoods U1 plus of G1 plus, U1 minus of G1 minus, and respectively U2 plus of G2 plus and U2 minus of G2 minus, so that G1 to the n attracts, moves everything outside U1 minus in U1 plus, and G1 to the minus n takes everything outside this open subset in the boundary towards U1 minus. And similarly, you see the same for G2 to the n and G2 to the minus n. So in fact, these two inclusions here guarantee that the group generated by G1 to the n and G2 to the n is a free group of rank 2, and in fact is a discrete subgroup of the whole isometry group of the D hyperbolic space. And the reason that this happens is the following. You might take point X, which is not in the union of all these open neighborhoods, and if you take a reduced word in the two generators, G1 to the n, G2 to the n, then you can see that by using these two inclusions, it always takes that point X in one of these neighborhoods. So simply like this is like can be verified, for example, for this word as follows. Like you can see that G2 to the n acts first on X, and it moves that in that neighborhood, and then that neighborhood is completely disjoint from U1 minus. So successively G1 to the 3n will act on that element, and it will move it in U1 plus, and continuing similarly, you can see that this reduced word in the generators will move X in U1 plus or minus, depending always on the sign of the exponent of the first letter. So for that reason, you can see that every reduced word cannot be the identity element. And similarly, if you take any infinite sequence of elements in the group, you can see that it will move the point X eventually away from itself. And that means that that sequence cannot contain a subsequence converging to the identity. So it means that simply that the group generated by these two elements is discrete. And we call this technique ping pong because simply the groups, the group element, excuse me, these two group elements play ping pong in the boundary at infinity of the hyperbolic space. And now we can define what is one Anosov representation. And the definition we give here, it's an equivalent characterization with the initial definition given by Labouri. And for that, we need the notion of the singular value. So if we take an element of PSLDR, we can form its singular values, sigma 1g, sigma 2g, and etc. And these are obtained as follows. We consider the matrix G times G transpose, and you can verify that this matrix is symmetric. So it is diagonalizable with positive eigenvalues, where here we like secretly mean like a representative of G, because G is inside the projective spatial linear group, but you can see everything is independent of that choice. So if you form this matrix, you can take the list of its eigenvalues. So Li denotes its ith eigenvalue, and the ith singular value of G is the square root of the ith eigenvalue of G times G transpose. And now, having fixed the notion of singular value, if we are given a finely generated group and a representation of the group in PSLDR, we will say that this representation is a nosov and the group is Gromov hyperbolic if and only if there exist gaps between the first and the second singular value of elements, which grow uniformly exponentially in the distance of the element from the identity element in the Kelly graph. So recall that ds here is a fixed word metric on the group gamma induced by a finite generating set S. So in fact, the second condition here implies itself for a representation that the domain group is Gromov hyperbolic and the representation is one and nosov. And automatically you can see that if the representation is one and nosov, then its kernel is finite and its image is a discrete subgroup of PSLDR. So in fact, if the group is torsion free, so it does not have finite order elements, then the representation is discrete and faithful. Okay, and now we would like to give you some examples of one and nosov representations. And let me mention here that we only gave the definition for one and nosov because this is the most general kind of an anosov representation. So basic examples include the Fuchsian representations. So by a Fuchsian representation, we mean a discrete faithful representation of the fundamental group of a closed hyperbolic surface inside the isometry group of H2, like orientation preserving, so inside PSL2R. So any such representation is one and nosov. And also if you consider PSL2R as a subgroup of PSL2C, so if you see now a Fuchsian representation as a representation in PSL2C, then you can perturb that representation, and a small enough perturbation of that representation, J prime, remains one and nosov and is also discrete and faithful. So, but what do we mean by a small perturbation? Like you have your initial representation and you have the image of your generators of the surface group. So you slightly perturb the generators, but always respecting the defining relation of the surface group. So as soon as you perturb them close by, you obtain new examples of representations, J prime. And as soon as this perturbation is small, the representation remains discrete and faithful. So this is like an example of a so-called quasi-Fuchsian representation. So here we have given you the boundary S2, which is the boundary at infinity of the three-dimensional hyperbolic space. And initially here you see the boundary of the two-dimensional hyperbolic space, which is exactly the limit, the so-called limit set of the Fuchsian representation J. But when you perturb the representation, now still J prime will preserve a topological copy of S1, but it's the new red circle here. Okay. And also other basic examples of anosov representations are Hitchin representations. So the definition is as follows. We consider the continuous irreducible representation of the Lie group PSL2R in PSLDR. And now we will call a representation of the surface group in PSLDR D Fuchsian if it is the composition of tau D with a Fuchsian representation. That means a discrete faithful representation of the surface group in PSL2R. And now a representation row of the surface group in PSLDR will be called a Hitchin representation if it is a continuous deformation of a D-function representation. That means there exists a continuous path of representation starting from a function 1 and ending to rho. And in fact, it is a very deep theorem of Labouri that every Hitchin representation is one anosov, and therefore it is discrete and faithful. So D-function representations are one anosov, and that's not that hard to verify by using the definition we gave before. But the theorem says that no matter how far away we deform from a D-function representation, the resulting Hitchin representation remains faithful. And lastly, I would like to provide you some examples of anosov representations coming from real projective geometry. Like so far, we have seen examples of surface groups, and we have in fact the following theorem, where it's proved by Benoit and also by Guissard and Winhard, like parts of it. And suppose that gamma is a discrete subgroup of the projective special inner group, which we assume it preserves and acts co-compactly on a strictly convex domain omega inside an affine chart of the projective space. So what do we mean by an affine chart? We mean the complement in the projective space of a projective hyperplane. So omega is a convex subset of that affine chart, and we assume it's acted co-compactly by gamma, by a discrete group gamma. Then Benoit proved in this case that the group gamma has to be Gromov hyperbolic, and Guissard and Winhard proved that the inclusion of gamma inside PSLDR has to be one anosov representation. And some basic examples arise by considering the D-dimensional real hyperbolic space as a strictly convex domain inside the projective space. And whenever we take a subgroup of isometries, which is co-compact, then the inclusion of gamma inside PSLD plus 1R is one anosov simply because gamma acts co-compactly here. And so it's a straightforward consequence of the theorem. And often, depending on the structure of the lattice gamma, these inclusions can be perturbed to give new examples of one anosov representations, which are Zariski dense. That means their image does not lie in a proper algebraic subgroup of, Zariski closed subgroup of PSLD plus 1R. And these are called Johnson-Milson deformations. So thank you very much for watching, and if you have any questions, feel free to send us an email. So thanks.